Yesterday we pointed out that metals have very high surface energies because of the fact that they are sharing electrons from several atomic layers beneath the surface, and therefore all those electrons are unsatisfied because they don't have an infinite number of atoms above them, or not an infinite number, but they don't have matching atoms above them, and they're at the surface, and so therefore they don't have as low an energy state as if they were completely bonded in the center or bulk of the material. And that's because of the longer range distance of attraction between the bonding of the metal atoms in the crystal. We also talked about friction welding, and we mentioned that you basically get lots and lots of shear and you're spinning it. One of the key things in designing a friction welding machine is to have a good brake, to have it stop. If the machine has lots of inertia, you can make the weld and then break it as you're slowing down, right? There is something called inertial friction welding. There's two types of friction welding machines, basically. One's a direct drive machine where you have a really big motor, and the other one is a smaller motor machine with a big flywheel to store the energy, right? And they call that inertial friction welding when you have the big flywheel. But in any case, it doesn't matter. Even if it's inertial friction welding, you got to have a good brake, because as soon as you stop the process, you've got to stop it quickly. Otherwise, if the machine's inertia just keeps on going, you break the weld right after you form it. So you have to be careful on that. Ultrasonic welding is a form of friction welding where you have very, very small macroscopic displacements. The difference here is you have huge displacements up here in friction welding. Ultrasonic welding is essentially the same process, but I have very, very low amplitude oscillations, and so your macroscopic displacement is near zero. You can't see anything with your eyes in general. The problem is it doesn't get rid of the contamination, it just displaces it, and so you get about a 50% bonded area in most cases, except that special case I told you about at Sandia. Friction welding, on the other hand, basically extrudes the contamination out of the joint. Now, there are other types of friction welding or forge welding or whatever. In fact, forge welding is one of the oldest welding processes. You know, as soon as they found native copper, they probably put it in a fire and beat on it and forged two pieces together, so far as that goes. We still use forge welding in a few applications, and one application is kind of interesting, is to think about the different ways that we join, and I used the boards wrong this morning, but anyway, let me come all the way down. The way that we join railroad rails. And a railroad rail, of course, has a cross-section, something like this, right? And you would like to weld the track together continuously. And the reason for that is if you have a joint in the track, as the wheel, the heavy wheel, comes across that joint, you don't have the same constraint as the wheel is rolling towards the edge as if it was a continuous piece of metal. You essentially don't have the symmetry around the joint, and you will get stresses that are about double on the ends. Even if it's bolted very tightly, when you're talking about something the weight of a railroad car, the bolts aren't going to keep some displacement from that. And so that higher load right on the surface will cause wear. And so if I'm looking along the joint, if this is my rail, which has the head up here, right? There's the head, and this is the base. So here's the base, and here's the head, right? And I've got it joined to trying to join. I don't have it joined, but I'm just bolting it. Typically on the web, they'll put some a bar in there with some joints. What will happen is over time, the head will wear right on the end, and now you go clack, clack, clack down the street. And I say down the street because the only time I've been on a really bad system was in New Orleans on the trolley cars, the old trolley cars. And you go boom, 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 boom. And you can tell it's related to the joint spacing, which at that time was probably only about 40 feet in the old days. Well, they don't like that because it means more maintenance. And so they now, most track is welded. And if you go out here to the subway in Boston, and as you're standing at the platform, if you look down, you'll see some welds. But there's different types of welds. One is basically a forge welding process where they take a bunch of oxyacetylene torches, just big flames, and they heat up the rail for about a foot on either side until it's glowing red. And they have this big hydraulic ram. And it's not a friction welding machine, it's a forge welding machine, and they just ram these two pieces of hot steel together. And they get flash, and they just extrude the hot ends out. I mean, it's hotter right at the ends. I mean, they place the flames so that you get the greatest heat right here where you want it, and you have a temperature gradient back here, but you're trying to get as much heat. Now, it takes about, when we get to heat flow, you'll be able to calculate this, but it'll take about 5 or 10 minutes to heat these big heavy rails up with these flames. So you don't make welds very fast. You make about, if you're in a production environment, not out in the field, but in a production environment where they're putting these things together, you maybe get 4 welds an hour off this machine, because you're just, the guy's standing around, you know, sweating, watching the tremendous amount of heat go up as gas from the flame. Anyway, they forge them together, and then they have a big hydraulic ram that comes along and just shears the hot flash off, because you've got this flash that extrudes out when you forge this thing together. And that's a weld. And if you go out and look at an MBTA line, what you would see in a case like that is you just see where the weld is, you'll see a bunch of sheared metal between the two joints here. Okay, you may or may not be able to pick it up. Not at least from standing on the platform looking down, and I wouldn't advise you to get off the platform. In any case, so that's one way they do it. And in fact, what they do when I say a production shop, they basically have a train that has got a bunch of flatbeds on it, and this train may be 100 yards long, could be 200 yards long, and they weld together 100 or 200 long sections, put them on the flatbed cars. That could be, 20 cars in a train, right, to go a couple 100 yards, and just make a big long string. That train goes out to where you want to lay the track, and they have a big machine that pulls the 200 meter long piece off the train, and then they make a weld in the field. Well, how do you make a weld in the field? Well, this is one. In fact, I went up to Bill Ricca once to actually see this, and I can't remember, there's a train company or MBTA was welding rails up there, and had this big long train. So you don't even have to go that far away. Another time in the field, I went over to Brighton, and they were repairing the MBTA tracks, and they had basically a big tractor trailer, and they would bring the big tractor trailer had a very large electrical generator in it, and this was diesel powered or whatever, and they would bring the two rails together and just barely touch them, and then pull them apart while applying, I don't know what the current was, maybe several thousands of amperes of current, and they would get an arc that would spark between these. So you first bring them together to touch, just barely, then you pull them apart just about 1/4 of an inch or so, and the arc forms. And in fact, it will start to melt things off. As it melts back, it will move down to an area where it's closer together, because the arc wants to be as short as it could be. And it will just kind of oscillate, the arc will oscillate back and forth, melting this thing off, and you slowly bring these things back together as the arc is melting it off. It's called flash welding because it looks like the 4th of July. It looks like a kid with his sparklers. Okay, there's flash going all over everywhere as this arc is blowing molten metal out of there, until you get the two edges completely melted, and then the ram squeezes them together. Now, in the oxyacetylene process, you may heat up red hot a 6 or 12 inch distance from the edge, and you're forging it together. In the electrical resistance method, you're basically only heating up something an inch or two deep. and it's really only melted, and you're not really forging at that place, you're actually melting the thing and squeezing it together. That's flash welding. The last type, well, people do actually stick welding, manual welding, if you've ever seen a welder holding an electrode. So it's not a good process for rails for various reasons.
Can you go back to flash welding for a second?
Yep.
How do you contamination on the surface?
Well, you melted the whole thing, and when you squeeze it together, you will hopefully push out that little bit of liquid that has the oxide on it. Now, in fact, flash welds typically will have some oxide inclusions that you don't get all of them out, okay? You won't necessarily get rid of all the oxides in this process either. I mean, typically rail welds can have some 1/4-inch inclusions of oxide left inside. But since most of the stress is right on the head, all you really care about is making sure you get a good weld up here. And sometimes they go in with ultrasonics afterwards to make sure they get a good weld, okay? You can go with stick electrode, but it's a very slow process. You have to preheat these types of steels to like 500-600 degrees Fahrenheit, so the guy is working next to an oven. It's not a very pleasant process. So stick welds, I've seen them in rails, but they're usually lousy. And there's different types of rails. I mean, right now I'm working with an engineering firm up here in Arlington to make rails for a large telescope that goes on top of a mountain in Mexico. This is, astronomical telescope, big mirror telescope, and this may be microwaves. But anytime you have a big microwave radar, you can have tracks that are 3 feet wide forged steel. It doesn't have a shape like that, but it might be a foot thick and 2 or 3 feet wide. And in general, they bolted those together. But it turns out some of these microscopes, in fact, this one is microwave because I think it's millimeter wave radar that's going on for, I guess, the University of Massachusetts and some other schools and people in Europe are building this $500 million or $100 million or whatever it is telescope. But some of these things are the size 100 meters across, okay, and so they're big structures, and they would like to not get the wear or even the bounce, because the tolerance on these things, in order to have good properties to measure the microwave radiation, the tolerance is 1/4 micron, which is 10/1000ths of an inch. Okay, and it turns out you can't stiffen this thing with bolting to get that. They tried miter joints and they tried all kinds of things. The one at, what's the one in something bank in West Virginia? There's this name of town bank that they have this big radio telescope for looking at the heavens, and they put miter joints in, and they've got problems with the bounce at the joints because it's mechanical joints. So this next one they wanted to weld, and it's taken about $100,000 worth of development work. In that case, they're doing something narrow groove arc welding, but that's a little bit different. But the other one I want to tell you about, the one that works cheap in the field, is thermite welding. And thermite welding, anybody know what thermite welding is? Anyone ever heard of it? Yeah, oh, Chris has. Okay, well, thermite, basically, here's your rail, and you take a steel bucket. I mean, this is not very fancy. I went down to Roslindale once to watch the MBTA do a thermite weld. So you take the steel bucket and you fill it up with this granular sandy powder. You have a little disc of aluminum right here. At the bottom is a valve or a gate. And the mixture is iron oxide, and let me just say it's Fe2O3. It could be Fe3O4, but plus aluminum metal powder. So you got an iron sand plus aluminum. And let's see, I haven't balanced this, but this is going to react to form Al2O3 plus iron. And let's see, if I do it this way, yeah, I'm glad I did Al2O3. Okay, it's balanced. If I'd done Fe3O4, it'd be a mess to balance, right? Anyway, I think that's balanced. Plus heat, because aluminum oxide is much more stable than iron oxide. And the heat will raise this whole thing to about 2,000 degrees centigrade in a fraction of, well, not a fraction, but in a few seconds. So all you need is a little blasting cap to ignite this pile of sand up here. All of a sudden, you start this reaction, and within a few seconds, you just see everything start to glow red because it's like setting off a little bomb, okay? I mean, it doesn't explode as a bomb, but it's a chemical reaction that generates a lot of heat. It obviously just melts through this little disc that's kept the sand from dropping down here. So the molten iron now falls in here, and you make a little casting. Originally, your rails were about 1 inch apart, and you put these little sand molds, which have the shape of the rail head. They're already pre-molded. Just clamp those up against the side, put the bucket on top, pour the sand in, start it with a blasting cap, stand about 30 feet away, because this does generate some sparks and stuff too. And all of a sudden the molten iron basically just drops right in there. No power requirements, you know, it's nice and flexible. The problem is you get about 50% defective welds where you don't get good fusion on one side or the other. So when you have 50% defective welds, it means you got to cut it out. If you cut it out, you got to put 2 welds in the part that you cut it out, and the 2 welds you put in each have a 50% probability of having a defect. And so you can see that this is a slowly converging series of getting a decent weld. But it's cheap. I mean, the equipment costs $100 or something to be able to weld these things together. It's fast. It doesn't require power. And when you're all done, you will see kind of, rather than a sheared edge here, you'll see a little rounded, little cone-shaped thing where they built up a little weld reinforcement. So that's thermite welding. Now, the great thermite weld experiment that I've heard about 10 universities take credit for this, but the MIT archives claims that it actually was MIT students back, I don't know, sometime in the first part of the last century, when there were trolley cars in more places. 5 MIT students, basically, as a prank, one of them got on and kind of fumbled for the change to keep the trolley car stationary, and the other 4 people set off thermite welds at the wheels and welded the trolley car to its tracks. And supposedly they all got expelled. I've heard like 10 or 12 different schools claim that prank, but apparently it was an MIT prank because it's a very fast process. I mean, you know, the melting all takes place in, you know, melting and freezing can take place in 1 or 2 minutes. So it doesn't take a long time to weld something together, as far as that goes. The Navy, for those of you that are in the Navy, has some problems with basically thermite reactions. Anybody know where the problem is on superstructures of ships? Right. In the old days, not in the new days, but you have a steel hull, and we know from the other part of the 3371 why we use steel, because it's cheap and stuff. But you don't want ships to be top heavy, so they used to build aluminum superstructures, and so they used to do explosive bonding, and maybe I'll talk about that in a little bit. But explosive bonding to bond the plates together. So you'd have an aluminum steel transition. You could weld to the steel on the bottom plate, and you could weld to the aluminum plate on top of this explosive weld. And so you have an aluminum superstructure, which is nice and light, and then you have a steel hull below that. The problem is, in a marine environment, aluminum and steel just cause a lot of corrosion, and so the iron starts to corrode and you form rust. Now you have aluminum in the presence of rust. Well, what's that? It's nothing more than the beginning products for a thermite reaction. And in fact, the aluminum can burn. We learned that, what was the ship in the Falklands? The Sheffield, the British cruiser Sheffield, got hit by an exocet missile. It wasn't a thermite reaction necessarily. Pardon me? No, it's not a Stark. This is Sheffield. This goes back when most of you were maybe not in diapers. This is the early 80s. Okay, this is the Falkland Islands War. Okay, but basically, the British cruiser Sheffield got hit by a Argentinian exocet missile, actually a French exocet missile that they had sold to the Argentinians, and the aluminum superstructure caught fire. Aluminum will burn. You can get a metal fire, and it wiped out the whole ship. So the British lost one of their main, I mean, this was a cruiser. They don't have battleships anymore, so this was one of the largest ships in the British fleet, and it was wiped out by one missile. About the same time, there was the Belknap disaster. Anybody in the Navy know about the Belknap disaster? You know about it? Or, okay, well, they were having maneuvers or something, or the Belknap was refueling at the carrier or whatever, and it turns out there was a collision, and this destroyer Belknap basically hit one of the elevator platforms, as I understand it, that had some aircraft on it, and the aircraft spilled some jet fuel, and we now know in the last couple of days what jet fuel will do as it burns, and it ignited the aluminum superstructure of the Belknap, and the Belknap was totally destroyed. And so, I mean, it wasn't, you know, not a lot of people outside the Navy heard about it, but basically we lost a destroyer, and the joke at the time was a gallon of jet fuel would wipe out any ship in the fleet. So in the mid-'80s, when I used to go down to David Taylor, the Navy Research Lab, one of the big things was to develop waffle construction steel superstructures, because now you'd have steel and steel, and you wouldn't have this, because the Belknap really was essentially jet fuel igniting a thermite reaction. Okay, it was the rust and corrosion that helped get it going. It wasn't just igniting the aluminum. So those are some of the problems you have with. Oh, now I guess since we're on cold welding, I could talk about explosive bonding. Explosive bonding was discovered basically in World War II. There would be some explosions and people would look at the damage afterwards, and they noticed some things had just been welded together. Pieces of metal got welded together in the explosion. And so after World War II, people learned you could take a big heavy plate, and you could put another plate at a critical angle, and the angle might be 10 or 15 degrees. It depends on what the two materials are, because we use this to clad other materials. So let's say this is a steel plate, and I want to put stainless steel or nickel-based alloy or something else on top of it, and use that as some part of chemical pressure vessel where I have the expensive material on the inside where I need it inside the vessel, and I have the steel on the outside for the strength. Well, it turns out there used to be two places. I think there's only one left in the world where basically you would line the top of this plate with an explosive, which kind of come as plastics and stuff. So you just put this explosive on here. You'd ignite it, and the plate would be forced against the surface. If you take high-speed movies, you actually can see that the plate gets slammed against the surface. So this would be in process. Eventually, it slams against the surface, and there's this critical angle. At that critical angle, you actually, from the energy of this mechanical impact, you actually get a little jet of your contamination being extruded out of that joint. And actually, you get little waves when you're all done. You actually get very, very good bonds. And kind of the hot gases being blown out of this thing during explosion, I guess, are removing some of the contamination or whatnot. Some of it's probably buried, but it's on such a fine scale that you end up with a two-piece plate. So you could have a very expensive material like tantalum is an excellent, has some of the best corrosion resistance for chemical processing of any material. It's very expensive. It's about the same cost as silver. So it's not cheap. You talk about the price per ounce as a few dollars an ounce. So you could put a very thin layer, like a 1/4 inch of tantalum, on a 3-inch thick piece of steel by explosive bonding. Now you have a bunch of plates, and you can form those and shape those and weld those different ways and make a chemical process vessel. DuPont had a facility in some valley in Pennsylvania where they used to do the explosive bonding. It turns out, I think they're out of business, but DuPont got in the business because DuPont's original business was making gunpowder in the Revolution, right? And all the big explosive manufacturing firms are all in the Pennsylvania, Delaware area because of DuPont and whatnot. So anyway, DuPont got into this after World War II, and I think about 10 or 15 years ago, I think they got out of the business. There's a firm out just outside Boulder, Colorado, who has a little canyon where they're called explosive fabricators. And they basically still do this type of business. Okay, you have to do it kind of an out-of-the-way canyon or place because the neighbors don't like the booms. It's also done when you're doing tube sheet welds in great big pressure vessels. In great big pressure vessels, you've got some heat exchanger. So the tube sheet, this is called the tube sheet. It can be a 12-inch thick. It could be 4 inches. Well, I've seen on little heat exchangers for a little diesel engine on a fishing boat. You might have a 2-inch tube sheet or a 1-inch tube sheet. But if you're talking about a great big boiler like down here at what's Boston Edison called now? Anyway, whatever, Anstar. Okay. You go to a place like that where you got a boiler twice the size of this room, you could have a 12-inch thick tube sheet, which is part of some great big pressure vessel, and the pressure vessel may have a 3 or 4 inch wall, right? And you have these heat exchanging tubes come through here, and they loop back around, right? And I could easily have 10,000 of these tubes going through this tube sheet. And the reason it has to be so thick is because it's supporting all these tubes and all the stresses, and it's full of holes. It's got 10,000. Well, it's got 10,000 holes in it, right? So you have water or whatever cooling fluid going through this, and then you have a fluid on the other side, and that's your heat exchanger. Well, you don't want any gaps between the tube and the tube sheet, which tube sheet is really a plate, right? It's a 12-inch thick plate. You don't want any gaps in there because you'll get corrosion. You get crevice corrosion. So they do all kinds of things. Sometimes they just weld to the top, and then they roll as tight as they can this thing to deform the tube against the tube sheet to keep any crevice from being there. But what's even better is to set off inside an explosive reaction. You have to get the right angles here on things and set off a little charge and do an explosive weld, and you get a weld all the way down the length. Now, what they do is they often kind of set this up and pull a little local vacuum on it, because that way the neighbors don't hear the sound. If there's, if a tree falls in the wood, does it make a noise, right? Well, if a tree falls in a vacuum, it doesn't make a noise. There is no air to transmit the sound waves, right? So sometimes people have set up things where they do explosive bonding in a vacuum. I've heard of this also for making things in a small little things in the precious metals business, where people want to put gold on brass or something for gold-filled materials. This is not gold-filled. This is titanium now. But in the old days, people used to make gold-filled, which is clad brass with gold plating on it. And I've heard of people who just had a little pressure vessel, not pressure vessel, but vacuum vessel, and they would do explosive bonding to clad the gold to the brass. Yep. In the case of the boiler, they basically just put a charge right inside the tube, and it's blowing it out up against the tube sheet. Tube sheet doesn't move. It's the tube that gets expanded against the tube sheet. They don't do that as often anymore. I think the rolling technology has gotten to be pretty good. So they go in there and essentially put a mandrel in there and just press it up against it. But in the old days, they actually did use explosive bonding.
Does that have to be like a timed explosive so it'll be certain angle?
Well, it turns out all explosives are timed explosives. Okay, the charge can't go any faster than the speed of sound, but you're right. They actually work out the composition of this to get the optimum velocity, because I have the inertia of this plate, right? And so to get all the force and everything, you have to, it's not just something you just kind of go and say, okay, I'm going to put some explosive on the surface of this and I'm going to put this at some angle. The angle is critical, the weight of the charge, the speed of burning of the charge, because you really do talk about speed of burnings in charges, okay? So yeah, you can call it timed, but basically you design your explosive so that it burns at the rate that you're interested in. But they do that anyway. I mean, even the airbags in your car, one of the problems, in fact, I could have brought that if I don't know, I was going to answer this question. I have in my office a little cylinder, which is just perforated steel. And it's got some, it's not asbestos, but it's got a refractory inside, and it's all wire wrapped. And basically, this little cylinder is part of an airbag system for an automobile, because the explosive charge, sodium azide, will go off in, let's say, a millisecond. I don't know how long it burns, but you know, the gas well, they don't call it explosive because they wouldn't want people to think that they have explosives in their car, right? But the gas generator, which is sodium azide, basically releases everything, burns in like a millisecond. Well, you don't want a millisecond. You want about 10 or 20 milliseconds, because the crush and the impact of the accident, you don't want to slam someone in the face in a millisecond, right? Force is dp dt, right? And if dt is small, F is big, you're going to break their jaw. So you actually want to have the gas come out a little slower. So they basically set this off inside this tube. The tube is perforated. It's got a refractory ceramic thing in there to slow down the gas diffusion, but also to keep the hot sparks out, because you don't want to burn someone or set off a fire because you got gasoline in the car too, right? So basically, the little airbag thing's a little more complex than most people realize, because you want the gas to leak out. And it's a fairly heavy cylinder, because you're going to generate probably 100 psi, or maybe even 300 psi. I don't know exactly, but if it's going to take 10 milliseconds to leak out into the airbag, and it would be generated in 1 millisecond, you got to get to about 10 atmospheres, right? Which is 150 psi. So I can estimate that these things are designed for a couple hundred psi. Is there a question over here? Yeah.
To the similar materials, then if you're going to subject these to thermal cycling, isn't that going to reduce stresses if the coefficients of expansion are different? That will.
Yep. Problem. In fact, I was going to talk about that in a second. In 3371, I was going to talk residual stresses today. But it's also an interesting question. What about the railroad rails we were just talking about? If I make a continuous 10-mile long railroad rail, and I get the diurnal heating and cooling. What's diurnal heating and cooling? Day and night, okay? Just a fancy word for day and night. Okay. But I get the heating and cooling. The sun comes down and beats down, or a cloud comes by. That 10-mile long piece of steel changes length by quite a bit, right? So what do? I have curves in the track. I mean, I could be going through Nebraska, but I guarantee you that somewhere they either have an expansion joint that allows for a fair amount of movement, and that's something they have to do a lot of maintenance, because that expansion joint is going to wear faster than other things, or they've got curves. If they just got a straight shot, then they're going to have expansion joints in there to take up the heating and cooling of these things, or the curves take care of the same thing. Anybody who's ever been past a military base and looks at the piping on the military base, I mean, they don't bury the piping on the military base. Why? I mean, you know, the gas pipe or something. You can say maintenance. Well, it's a different type of maintenance. If someone you know, in World War II, when people would come and bomb things, if you had buried the pipe, it's a pain in the neck to go and repair that when it's buried in the ground, if you break it. You know, if someone comes and bombs something, and a bomb's going to wipe it out, 3 feet underground as well as 3 feet above ground, it's a lot easier to repair it if it's above ground. However, and I grew up in high school in Virginia Beach, Virginia, and I remember the first time I'd drive by the Dam Neck Naval Base or something on the highway, you'd see these pipes, and sometimes they'd be going over a little creek, and you'd see the pipe come along, and it goes up about 4 feet, and it comes across, and it comes down, and I figured, well, they were just doing that to go across the creek. Of course, that didn't really make any sense. And then I noticed they did this out in the middle of nowhere, where there was no creek. About every 100 yards, the pipe's running about 3 feet off the ground, and they take it up 4 feet. They go across about 10 feet, and they come back down about 4 feet. Why? Thermal expansion. Why don't you have to do that in the ground when you're 3 feet deep? Because the ground doesn't change temperature 3 feet deep. The temperature of the ground 3 feet deep, just about anywhere, because of the insulating value of the soil, doesn't change but about 2 or 3 degrees over the whole season. It certainly doesn't change temperature overnight because it's insulated by the dirt. But that's why they have, I mean, they run it above ground because it's easy to repair after a bomb attack, although those are different types of bomb attacks, okay? Nowadays, the bombs are bigger. But back in World War II, you know, when they probably designed that system, or just afterwards, when you had smaller bombs, you wanted to be able to get to things to repair them. So thermal expansion can be a big problem on lots of things. And you're right, when I clad these plates together, I have to worry about the thermal expansion. But in fact, they do all kinds of things to take care of that. And some of that, they can introduce residual stresses into the structure intentionally to account for the fact that when you heat the thing up, it's going to generate its own stresses that will have to counteract that. So you may intentionally pre-stress the material. But we do that all the time. I mean, pre-stress concrete. I mean, concrete is a composite in most cases. Structural concrete is a composite. In most cases, we put steel reinforcing rod in it. And they have what they call pre-tensioned concrete or post-tension. They have pre-tension and post-tension concrete where they have steel cables in there, and these steel cables can be 300 KSI steel wires. And they basically can make a much lighter concrete structure because instead of just a steel rod that's not under tension, they can basically put a tension on these things. If they put a tension on it, they're going to be putting the tension on the compressive on the compressive side, right? I guess, or whatever, of the beam. That 300 KSI is the tensile strength of the steel, but they're running these things up in service. I mean, it's 300 KSI is the tensile strength of the steel, but they may actually have them loaded to 60% of that. And now you run into the problem, they have them coated with plastic and stuff, and there's some fairly serious problems where some of the plastic coating didn't get put on properly, and they start to corrode, and you get, at those levels, you get stress corrosion cracking. And so now you have some fairly major structures that have to be repaired or torn down because once it's cast in concrete, it's cast in concrete, right? You can't repair it very easily. So, but post-tension and pre-tension concrete structures are fairly common, and they work just fine in most cases. Okay, most cases. And it's not usually a catastrophic failure because once one cable breaks, you got multiple cables in there. Basically, you'll start to see concrete start to spall off and stuff, and you know you have a problem. Okay, but it can be an expensive problem, particularly if you have to tear down the building to repair it. So. Yeah. Yeah, in fact, heating up these rails will definitely change the metallurgical properties. The thing is, the cheap rails, it's not a problem because most steel rail is just hot rolled steel. And so, if anything, you're liable through cycling up above the transition temperature of the steel. Steel has this interesting property that it transforms crystal structure at about 723 degrees centigrade, approximately. And when it retransforms, you can actually get a finer structure, and that's one of the reasons why in low carbon steels, not super high strength steels, but in low carbon steels, you can weld them and get almost the same properties in the weld that you can in the base material because you have this beneficial phase transformation that actually can improve the structure of the lower strength steels. It turns out the rails are high strength steel, or not high strength, but high carbon steels. They're about 1% carbon, which makes them a pain to weld because you can get hydrogen cracking. We'll talk about later in the course. But you'd like to get them nice and hot to drive off any moisture so you don't get the hydrogen entrapment and hydrogen cracking in these things. But in general, there are heat-treated rails, but the vast majority, and I'm saying, well, in the old days it was 90%, or actually it was 99% of the rails. If I go back to Andrew Carnegie, and they were building rails, across the country, they were all just hot-rolled rail, and you couldn't destroy it by heating it up. It had been hot when it had been formed, and it has a coarse grain size and basically lousy properties to begin with, and you can't degrade them much more. Nowadays, more and more, and I don't know what the percentage is, it used to be like 10%, but it wouldn't surprise me if it's not 20, 30, or even higher percent now, they use heat-treated rail. Now, one of the rails they used to use was a 1% chromium, which was not a heat-treated rail, but at 1% carbon, the rail structure is basically what we call perlite in steel, which is a mixture of iron and iron carbide. It's a very, very fine composite. And adding chromium to it gives you a much finer structure. And you get much higher hardness and much better wear resistance. But 1% chromium is expensive. I mean, you can take something that costs $300 a ton, and you may add $50 or $100 a ton to it, just for adding that 1% chromium. But you might double or triple the wear rate. They do have heat-treated rail, but that's less common. More and more of the rail, 10 or 20 or 30%, is this chromium rail, and so it's not, the steels are not generally heat-treated to give them exciting properties. Now, that's not true of this radio telescope that's going up on the mountain in Mexico. Those are basically 20 sections that are forged. I can't remember, I think it's like 30 inches by 10 or 12 inches as just a solid cross section. It's forged into an arc that is about 80 meters in diameter or something. I can't remember. Maybe it's 60 meters in diameter. So there's like 20 sections they have to weld together. They're going to do arc welding on that. That is a heat-treated steel. That steel has a strength like HY130. It's essentially an HY130, 130 KSI, quenched and tempered steel. But that's just because of the weight of this huge thing. And the problem there is they often double joint sections, whether you're talking about railroad rails or whether you're talking about pipelines. Typical pipe length for a big 40-inch or 48 diameter pipeline, the standard length is 40 feet. But typically, because you can get a tractor trailer and make it a little bit longer, you can make an 80-foot trailer. They basically will make a shop weld and put two of them together. They'll what they call double joint the pipes. And then they'll take the 80-foot sections out in the field because the field welds are more difficult to do. In this case of this track that has to go on the mountain, you're up at 14,000 feet. And so they qualified the procedures in Chicago, at this welding shop in Chicago. Before they actually make the real welds up on the mountain, they actually have to remake the welds up there because at 14,000 feet, you're about 0.7 atmospheres. And the arc characteristics change. We'll get to that when we get to arcs. And so there's lots of things that can change when you start doing things in different conditions. Okay, so there's lots of different types of rail. There's not lots of different types of rail steels, but in general, the rail steels are not very sophisticated steels. Now, the ones for this radio telescope, it's a more sophisticated steel. But most of the things that are taking passengers or freight, railroad tracks, it's steel technology from 80 years ago. Okay. Other questions? Yeah. Right. This is for rail you're thinking about? Whether you can do zigzagging or dovetailing. The problem is if you go through the stress analysis, as long as you have a mechanical joint, it's going to move on you. Okay? And in fact, I've seen that stress analysis for these telescopes. And there's no way around it. And people try to come up with different things. Now you can say dovetail. Well, maybe you dovetail this way, you mean? How they interlock this way? Well, the problem is you're going to run into stresses that are going to cause fatigue on these things. In the direction of, you mean the other way, perpendicular to that? Vertical stripes, kind of a waffle or a corrugation vertically. If this was a corrugation vertically. Well, they tried miter joints, and that's just a variation of me on a miter joint, and miter joints don't work. They have miter joints in this radio telescope in West Virginia that, the miter is like 3 feet long, and the contact area of the wheel is only like 8 inches wide. And so, but even so, when you go over that, the asymmetric loading causes enough at the interface. There's still got to be an interface, and asymmetric loading kills you. Okay, the only way people have really been able to, when you're carrying such heavy loads, the only way to do it is continuous, homogeneous, relatively homogeneous material. I'm sure people have thought about a number of, the simple thing, the cheap thing is mitering. I'm sure people have tried to think of whether they can corrugate it or interlock it, dovetail it, like you say. But you're going to, aside from increasing the cost of machining, you're going to end up with some fatigue problems because these things are fairly heavily loaded. The stress on these ones for Mexico, the contact stresses, the bearing stresses, about a half an inch beneath the surface or an inch beneath the surface, are about 120,000 pounds per square inch. So it's a problem. I mean, the steel's only got about 140,000 pounds per square inch, but it's in compression, so you don't have to worry about it. In fact, the way we saved a lot of money, it turns out this is an international project to build this thing, and the Germans originally spent $100,000 making one test weld, and they did it with stick electrode, and it took them a week to make this weld. And that was because they took this whole huge forging, and they basically they beveled the edge, and they just put thousands of weld passes in here. And they did it, it had to be preheated to like 300 degrees Fahrenheit. So the guy's sitting next to an oven, and this is not a small oven. I mean, this weighs tons, right? So it's radiating back at him, and he's putting in thousands of weld passes. That's why it took a week. It took several guys a week to just put the weld metal in. Well, what we've done, just looking at it sideways, it turns out that we found someone that can do narrow gap welding, and this thing is 10 or 12 inches thick. But it turns out the contact stresses where the welds are going to be are only in the top 2 inches. And then I think we got about, I can't remember, it's 4 inches or 6 inches below that. And then we put a 2-inch thick steel plate down here, and we weld this thing before we weld the joint. And when we're all done, we don't bother to weld this because the stress analysis said, you know, it's a great big wheel that's rolling up above here. The contact stresses, though high stresses, are only up here. The stresses down here like 10 or 20 KSI, even without a joint. And we can support that by just a 2-inch plate, fillet welded on the bottom. The problem is you're going to have defects here, so what do? We make the weld, and when we're all done, we drill I think it's a 3/4 inch hole. We just drill out the root, 30 inches deep. Okay, so now we've just reduced our stress concentration. And it turns out if you get 6 inches deep down here where the drilled hole is, the stresses are down to like 25 KSI. 25 KSI and 140 KSI material, you'll never get fatigue. You're below the fatigue limit. If you want to see the stress analysis, I got it down on my desk. Okay, or did I throw it away? Anyway, but I can get it for you if you want. And I know I trashed the email that had them, but anyway. Okay, is that, we're about done. Unless someone's got one other 2-minute question. We'll get to semiconductor joining tomorrow, which is sort of a far cry from railroad rail welding.
Yeah, I got a question. I don't know much about materials, so tell me about when you build that hole,
Yeah.
what are you getting rid of?
I'm getting rid of well, at a root pass, when I'm doing an arc weld, and I put this root pass in, they call it the root pass because it's at the root of the weld. This is the face of the weld up here. But when I put that first pass in, I've got lots of heat flow, and I don't have a great geometry, and I will typically end up with some lack of fusion defects when I do that. If I wanted to get a full penetration weld, and I'm going to weld from the bottom side on a heavy plate, what I'll have to do is I'll have to go back in and I'll have to gouge it out. And I can either do it by grinding to take out the defects that are the lack of fusion defects that are there, where the metal didn't melt together properly, kind of overlapped cold and solidified against it without a weld. I either have to grind it out or I have to air arc gouge it out. Now, air arc gouging is a wonderful process. You'd love to do this, especially on the 4th of July. You take a carbon tube, you hook some compressed air line up to it with a little valve, you put it in a stick electrode holder, and you strike an arc with this carbon tube in the groove. Then you turn on the compressed air, and the arc melts the metal, and the compressed air blows it out. So you got sparks going all over everywhere, okay? You're basically cutting a groove through the material. And you can do it really quick. I mean you got several hundred amps melting metal. And what you're doing is you're burning out the defect, and now ending up with a nice, on the back side, you end up with a nice rounded groove. And now when you put the weld in there, without any sharp corners, you get good fusion all the way around the root, okay? But if I want to make a defect-free, full penetration joint from both sides, because it's a thick piece of steel, I'm going to have to either grind or air arc gouge out the defects at the root, because when I originally designed that thing, I have kind of a sharp corner, and the metal doesn't get down there and fuse like it should. And so standard process is what we call back gouging, grinding or air arc gouging. If you cut a fillet, but now you got to machine it, okay? If you want to make a J groove, you can make a good joint. If you want to machine what we call a J groove rather than a bevel, you can make a good joint without doing some of that. But the problem is that's expensive. I can plasma arc cut or oxyacetylene cut a flat edge very, very inexpensively. If I got to go in and machine an edge, I probably just increase my cost by a factor of 10. Okay? So it's a matter of cost on joint preparation. Okay, thanks. And if you didn't get one of the Pentium chips, we'll talk about these tomorrow, but I have spares to give away. If you'd like one, take it home and impress your friends with your tab tape.